Okay, well, let me say something about the main of the main subject of the course. It's not clear whether it's K-theory or C-star algebras, because it's not a course just on K-theory. You can have a course on K-theory. There are many different kinds of K-theory. There's K-theory as it's applied in algebraic topology, which is closely related to the C-star algebra one. Then there's what's called algebraic K-theory, where you don't just have well, in any setting whatsoever, K0 is a purely algebraic construct. Can be for a Banach algebra. Everyone know what a Banach algebra is? It's an algebra over the complex, real or complex numbers, with a norm, certain properties, and it's complete. If if you have a Banach algebra, then there's what's called could be called Banach algebra K-theory. Sometimes it's called topological K-theory, but that's I think that's confusing because it refers to the applications of K-theory to topological spaces, which is basically commutative Banach algebra, continuous functions on compact O-star space. All right. But so as I said, K0 is a purely algebraic concept, even for a Banach algebra. You just look at the algebra, or even just the ring structure. And but if it's if you're looking at K1, then this is for a Banach algebra. Then this is uses the topology of the Banach algebra. So that's why I like to call it Banach algebra K-theory. So it's not because that's clearer, I think. Or it could be C-star algebra K-theory. But if you're talking about C-star algebra. Okay, but so there's K0 and K1 and K2, K3, and so on for Banach algebras. But this now I'm going to make a statement I don't really mean. This is not really very interesting because if it's a Banach algebra over the complex numbers, then you have K0 and you have K1, and that's it. K2 for the Banach algebra is exactly the same as K0. Okay, this was discovered by Raoul Bott, who was a Canadian. Well, he was educated in Canada after 1968. He arrived here, then Czechoslovakia. But and then he, when I was a postdoc, I met him because I was at the Institute for Advanced Study as a postdoc, and he was there as a visitor from Harvard. I remember mentioning to him that I was interested in applying to a vacancy, a job position that had been advertised at Harvard, and he was in the lounge at the Institute, Paul Hall, and he was encouraging. He said, "You better move quickly." I guess I was getting okay, but now if it's a Banach algebra with the real numbers, then almost the same thing happens. But you might say again with the with tongue in cheek, it's. By the way, I don't think I can talk with my tongue in my cheek. But anyway, if it's a real Banach algebra, then you have K0 and K1, and then K2, which is different from K0 for real Banach algebra in general. And then K3 and K4, K5 keeps on going like this for a while. How many people have heard where it stops? Okay, Rishi, when does it stop going? Yeah, so you get K0 so up to K8, which is the same as K0. So Whether it stopped the step before or there, it's hard to tell. Okay, that's a matter of that's a judgment call. But then it just repeats. So again, that's spot periodicity. But notice that notice that 8 is a multiple of 2. Okay. Again, you might think that's not a very deep comment, but also notice that a complex Banach algebra is an example of a real Banach algebra. Okay. So because the complex numbers are an algebra over the real, so they contain the real number. And so if the groups, if these k groups for a complex Banach algebra alternate k0, k1, k0, k1, and so on, for the k0, k1, k2, k3, and so on, then if you look at the real k groups, there has to be it has to mesh, right? Yeah, because otherwise, eventually you have them all the same. They all have to be the same. This, by the way, I noticed once that the certain insects, I think cicadas in particular, their underground stage lasts a certain number of years, sometimes quite a few years, even more than 10. But it's always a prime number. Okay, so there's an exercise in K theory in biology. Okay, why is that? Of course, even when they're underground, they have predators, but they especially have to worry about when they come up above ground. They don't want to have someone that knows when they're coming up and is ready for them. Because it's hatched around the same time. Well, some multiple. Well, okay. But then there's this algebraic K theory, which is very important. Turns out in C-star algebra theory. So there's an algebraic K1, and it's related to the Banach algebra K1. If you have a Banach algebra, it's they're both groups, right? The algebraic K group is a group, a abelian group, and the Banach algebra K1 group is an abelian group. Well, the algebraic K1 group maps onto the natural map onto the Banach algebra K1. Okay, well, but maybe I should just say a few things about Banach algebras and C-star algebras. I don't know how much without independently of K theory. I'm not sure how much people are familiar to what degree people are familiar with Banach algebras and C-star algebras. But by the way, the simplest example was just scalars, the complex numbers, or the real numbers. Generally speaking, in this course, we'll be looking at the case of the complex numbers, because ironically, perhaps the complex numbers are less complex than the real numbers, because they're algebraically closed. Okay, but so you have so that's a Banach algebra. It's a C-star algebra. Complex numbers are a C-star algebra. What's a C-star algebra? Well, the most straightforward definition is you look at the Hilbert space. Everyone know what a Hilbert space is? If it's finite dimensional, then it's what's sometimes called an inner product space. and with this over either the real or the complex numbers. Perhaps in most undergraduate mathematics, you think of a Hilbert space, an inner product space over the real numbers, but it just as well be over the complex numbers. So if you have the, for instance, the algebra of complex numbers itself, or sorry, the vector space of complex numbers, it's a complex vector space, then what is the natural inner product that makes it a Hilbert space? Are you familiar with that? Yeah, well, it makes it, how do you make the real or the complex numbers into an inner product space? Well, are you familiar? Have you studied linear algebra? Yeah. Okay, well, sometimes, so on Friday when I was talking about linear algebra, I meant over an arbitrary field without talking about specializing to the real or complex numbers. But usually in a linear algebra course, one looks also at the special case, if not exclusively, then at least also at the special case of real or complex numbers, right? Usually real numbers, maybe. Okay, so if you have a real inner product space, well, the real numbers are an example, I guess, of a real inner product space, right? Okay, but for something to be an inner product space, there has to be an inner product, right? So what's the inner product? Sorry? Yes. Yeah, okay. In fact, you could be even more somehow, you could make it into a little rhyme and say the inner product is the product. Yeah, okay. Right? Well, yes, but you don't have to be, you don't have to go into gory details. It's a product is usually bilinear. An inner product is by axioms, and an ordinary product, well, if we know what the ordinary product is, and it just happens that the ordinary product satisfies the axioms for an inner product, if you consider the real numbers as vectors, right? Okay. Now, are you familiar with the case of the complex numbers? All right. So now that's a sort of a very concise statement. Is that clear to everyone? What is your name?
My name is
HY. All right. Okay. Does everyone understand what HY said? That I mean, what did he mean when he said you take the complex conjugate? Yes. Yeah. Right. So you have two complex numbers. You consider them as vectors in this one-dimensional complex vector space, and you don't just multiply them. That would be some kind of bilinear product, but it wouldn't be what's called inner product. It wouldn't be a Hilbert space or inner product. But as you said, if you take you have to choose your convention. You take the first one or the second one to take the complex conjugate of it, and then you take the product. Okay, and that satisfies the axioms for inner product in a complex vector space. Okay, well, and in finite dimensions, in the norm associated with the inner product, and it's called the 2 norm. You take the norm of a vector square. You take the norm squared of a no. You take the inner product of a vector with itself, and then you call that the square of the norm. Okay, in other words, you define the norm as the square root. One of the axioms is, of course, this is positive, and even non-zero if the vector is non-zero. Okay, so that's how you get the complex numbers to be a Hilbert space. And what's the algebra of operators, linear operators on the this Hilbert space? Are you familiar with linear operators? Okay, but on Friday I was talking about linear algebra, right? Well, already in linear algebra, you have linear operators, right? You have matrices, but they're not. They also have linear operators, and they're not quite the same thing. So if you have a vector space, then you don't have matrices automatically, but you do have linear operators. They're maps from the vector space into itself. Which remind me of your name. I think on Friday you told me your name, but Chris. Chris. Hey, I'm sorry. Okay. I'm not very good at names at all. Okay, so linear operators are mapped from the space into itself, considered as sets, and then it preserves structure, which means the scalar multiplication. It's compatible in a natural way with scalar multiplication of vectors by numbers, by scalars, and it's compatible with addition in the natural sense. So it takes the sum of vectors into the sum of what it takes the two vectors into. Does that make sense? Okay, well, that's a linear operator. That's called a linear operator, either between two vector spaces, linear operator or linear map, or linear transformation, many different names. And okay, but you have two of them, you can compose them. Also, they're related to matrices. Do you remember? You probably studied it at one point. But do you remember how linear operators are related to matrices? Yeah, exactly. Yeah, the rule for multiplying matrices comes from the natural multiplication of operators, where you just first do one, then you do the other. You operate with one, then you operate with the next one. That's called the product of the two operators. But then every operator, if you fix a basis for the vector space, let's just say we're talking about the case where the vector space, just one vector space at the moment. We're talking about linear operators from a vector space into itself. All right. If you fix the basis, say it's finite dimensional, so you have a finite basis. Well, then you have every operator has a matrix, right? And you can tell from the matrix how the operator acts on a vector, because the vectors have matrices too, if you like. They have column matrices. That's the usual convention. You multiply a column matrix by a square matrix on the left, and if it's a square matrix of an operator, then what you get is the column vector of the operator acting on the original vector. Okay. So so if you if you interpret the matrices this way as corresponding to linear operators, the matrix multiplication corresponds to composing the operators, considered as maps from the space into itself, right? Okay. But then this is how you get matrix multiplication. It's, no one in their right mind would think of any would have any other reason to multiply matrices the way you have to learn it, right? That's, I mean, the proper way to multiply matrices is to just multiply the entries. And actually, that's interesting. People do that. Okay, it's called Schur multiplication. Schur is famous. Schur. Okay. But so the yes. Well, I would say that that's an interesting question. Oh, okay, right. Yeah.
Does K-theory work for nonlinear operators, or is it only mostly available?
Okay, I could hear that just fine, but that's maybe recently I got hearing aids, okay, and maybe they're even more than I need. Huh. Okay, but Rishi, was that how was that the second time?
I was okay. That the Zoom is better.
Of course, there's noise in the room. Yeah. Sorry.
But if you repeat the question, that'll be easier.
Oh, yeah, okay, well, I'm always hesitate to steal someone's thunder, to try to steal someone's thunder, but, okay, so what was the? Okay, oh, non-linear, so in this course, we're basically going to be talking about linear operators, okay? And maybe that's a question to think about. Why do we just look at linear operators? But but for one thing, we're looking at vector spaces, right? And normally when you look at a mathematical structure, if you're looking at maps from it into itself, the natural thing is at square one, so when you start off, is to look at maps which preserve all the structure of your space. Okay, so if it's a set, then it doesn't even make sense to say it's a nonlinear map, right? A map from a set into itself. If it's a vector space, and you have a map into itself, well, one reason linear maps are interesting beyond the context where you assume the map is linear, well, this is what calculus notices. Newton and Leibniz, lots of people noticed at a certain stage that a nonlinear map can be approximated by a linear map, right? And again, when I was at the Institute for Advanced Study, I remember trying to convince one of the visiting members who had specialized in English literature. I tried to convince her that this was true, that you could approximate an arbitrary map, a nonlinear map, with just a curve like this. You could approximate it by a straight line, and that would be fine. She wasn't. She was worried about that. Okay, and now I could see ways to be worried because it only works at that one point, right? And maybe I didn't say that clearly enough. Okay. Otherwise, it gets pretty bad pretty quickly, right? Okay. But anyway, that's oh, it's a good question because nonlinear phenomena are all over the place. But the functional analysis and operator algebra theory sometimes looks at considers the nonlinear setting, but in a very careful way. I mean, have to be careful not to go beyond your what you can manage. Okay, well, thank you. Yeah. By the way, you could look into this yourself, and but the particular question by the way, so how do linear mappings make an algebra come into being an algebra? Well, you can the multiplication of linear mappings is just composition, which makes sense for nonlinear maps too, right? But if you want to add two linear maps, then it works quite well because you get a linear map. You add them vector-wise, right? You add the values for each vector, and that gives you a new linear map. Now, of course, if it's two nonlinear maps and you add them in the same way, then you get another map, which of course will also in general be nonlinear.
Can some of them be linear?
Well, for instance, if one of them is minus the other, then you get 0, right? Well, okay, but I wouldn't boast about that. But I wouldn't crow about that, especially. No, the point is that you get an algebra of linear maps, and this algebra is so for instance, if it's a finite dimensional vector space of say dimension 2, then what's the algebra of linear maps in terms which you can visualize? Well, you choose a basis with 2 elements, then you're going to have square matrices representing the operators. those are called 2 by 2 matrices sometimes, right? Okay, and multiply 2 by 2 matrices, those form an algebra. And that's, if the scalars are real or complex, then that's an example of a C-star algebra. And with a suitable star operation, which is the, well, I'm talking about the axiomatic approach to C-star algebras, where you just say you have a star operation, a certain property. In the Hilbert space, every bounded linear operator, bounded is automatic in the finite dimensional case. Every bounded linear operator has a what's called an adjoint. Well, in fact, for every finite dimensional vector space, every linear operator from the space into itself has an adjoint as an operator from the dual space into itself. But over the real or complex numbers, there's a very close relationship between the original space and the dual space. They're almost the same thing. So the adjoint operator in general in the dual space exists in the original space, and you call that a star, call that the star or the adjoint, and that is well, you can extract these properties, and you get the abstract axioms for C-star algebra as they're outlined in the textbook. And then getting on to a century now, in the early 1940s, Gelfand and Naimark showed that the axiomatic that you can characterize C-star algebras by looking at the properties that the concrete algebras in the Hilbert space, algebras of linear operators in Hilbert space, the natural properties that they have, and taking those as axioms. So you have an abstract algebra. Well, usually, as I said, the complex numbers are less complex. So you look at a complex algebra, which is a vector space with multiplication, suitable properties, and the norm, and this, you assume it has a norm, and a star operation, all with certain properties. These will be detailed in the textbook, and they proved that if you have a abstract, it's called a star algebra, with it has well, it has to be with the norm. There's supposed to be a norm which is tied in with the product structure and the star structure, as a C-star algebra property as well as a normed algebra property. So look at all these axioms for the normed star algebra, including that it should be complete as a Banach space. Well, okay, but this abstract star algebra is isomorphic to it means all structure gets carried over to a concrete algebra of operators on the Hilbert space. So star algebra of operators on the Hilbert space means that for every one, if you have an operator in the algebra, then the adjoint operator is also in the algebra. Okay, but this is and this was, well, yes, question.
Okay, if I follow the classic question, I have a-
Well, you got some data on your earlier question already?
No. This is actually kind of unrelated question about C-star algebra.
Yes. Okay.
Because I have Gelfand.
Well, may I just, I'd like to, I mean, I'm supposed to be registering participation in the course, right? So if you meaning good questions and so on, and well, let's say questions, and it's a matter of opinion how good they are. But so if you,
I can wait to the end of the class.
okay, fine. Sure, but oh, for the question or for the name?
Both.
Okay, fine. But now you've got me on tenterhooks. Yeah. Okay. All right. But I would like to welcome, in general, I would like to welcome questions. Um, the, um, the, the sum total of material, if you like, to be covered in the course is flexible, and that's not so much the point as somehow getting people interested in the subject and getting some idea that there's something going on. Okay, so and there there really are this area of mathematics, which is less than 100 years old. Before mentioning Gelfand and Naimark, I should have mentioned von Neumann. Well, there's some name dropping in the emails that you've received, sort of repeating ones from last year, but the subject doesn't change enormously from one year to the next, right? Actually, sometimes it does. There's one of the main sort of items in this course is what's called classification of C-star algebra. And well, what does classification mean? And that's one of the things I want to talk about at various levels, going back to what James Glim did some 60 years ago, to what has been done very recently. The various classes of C-star algebras. A really nice classification has been obtained. And you might say, what is the purpose of this? Well, one theory which I've seen advanced is that the main purpose of the brain is to classify things. Okay, sorting things, and so if someone shows that something can be done in that line, that direction, then we should be grateful, right? Instead of just training to do it, because sometimes it might not be possible. Well, of course, sometimes classification is not necessarily a good thing, because if there's we and them, too much of we and they, then that's not always good. But well, so where does the first classification for C-star algebras start to click in? Well, what about these matrix algebras? There's 1-by-1 matrices and 2-by-2 matrices, say over the complex numbers, and 3-by-3 matrices and 4-by-4. Okay, and these are algebras, C-star algebras. Let's consider them just as algebras for the time being. In other words, complex vector spaces with the multiplication. So, of course, intertwining with natural intertwinings between the addition and multiplication. Well, you have to prove it, but it's true. It's true if you look at 10-by-10 matrices and 11-by-11 matrices. As algebras, these are different. Okay? That's a good exercise. Actually, there's an easy way of doing it. You want me to give you a hint? Or yes? Sorry, what? Yeah. Okay. Well, if you're for any class, any kind of mathematical structure, then if you have two examples of it, it makes sense to say, well, different is sort of slang. It makes sense to say that they're isomorphic or not isomorphic. which is Greek for same shape, okay? But it goes beyond the shape. It means they're essentially the same, okay? Isomorphic. Everyone seen the word before? So isomorphic vector spaces is a theorem that says that isomorphic vector spaces are isomorphic if and only if they have the same dimension, right? Okay, and that's a theorem that every vector space has a dimension. In fact, on Friday I was talking about linear algebra. That's one statement of the main fact about linear algebra, that the dimension exists. Okay. Well, of course, fake dimension exists. Much easier to prove that, and it has the property, the fundamental property of dimension, that it's additive on direct sum. But it's still true for fake dimension that two vector spaces are isomorphic if they have the same fake dimension. But it's a good exercise to see if that's any easier to prove. I think it might be. Well, okay, but by the way, this comment about the dimension of a vector space and they're isomorphic if and only if the dimension is the same. I'm slipping this in I'm trying to slip this in inobtrusively as a hint for the exercise about the matrix algebra. Okay? Anyone, how many people are catching on to that as a hint, as a possible hint? Okay, so the idea is we have these square matrices, algebras of square matrices, maybe 10 by 10, 11 by 11, and we want to know if they're isomorphic as algebra. That means essentially the same. There should be a map between them, which is bijective as a set map, on and one to one and on to injective and surjective. And furthermore, both it and its inverse preserve are additive and preserve multiplication. Okay, and preserve also scalar multiplication too. They preserve all the structures. Okay. If that's true for two algebras over a scalar field, then they're said to be isomorphic. Okay, but in particular, if they're isomorphic as algebras, okay, let me go ahead, and you're going to have trouble enough as it is doing all the exercises. So, or even doing some of them. I mean, even picking out some to do. So let me. By the way, I hope you take seriously Mr. Lau's advice how to approach the problems. Okay, he's given some very nice suggestions how to do problems. You can make up your own problems if you want. Okay, but if two algebras are isomorphic as algebras, they have this linear isomorphism between them that preserves product. Well, in particular, it's a linear isomorphism, right? And the algebra among, if you just look, forget temporarily about the product, what is an algebra? An algebra is a vector space with a product. Right? So if you forget about the product, it's just a vector space. And if they're isomorphic as algebras, they're going to be isomorphic as vector spaces, right? Because it's a bilinear map. It's a bijective map, which is linear in both directions. Okay, so and preserves product, but in particular preserves the linear structure. So the vector spaces are isomorphic, and we know when vector spaces are isomorphic, right? You just have to compute the dimension. So what's the dimension of the vector space of 10 by 10 matrices? Okay, well, I've got two answers now. What do you have an answer? Yeah, okay, yes, that's 2-to-1 now. It's like a tennis game, okay? That's topical because we just had a nice tennis final on the weekend. Well, well, a whole bunch of them. Of course, I'm not suggesting everyone gets glued to their television set way we do. But Okay, and now you see, okay, 10 by 10 is 100. What about 11 by 11? And now we're getting, we're sort of coming across the phenomenon that in mathematics, not only is there a conceptual challenge, but sometimes there's a technical challenge as well. Okay, so now nobody, and furthermore, when I was in school, we learned our multiplication tables up to 12. Okay, so I know what 11 times 11 is. But anyway, we don't have to think very hard to guess that it's going to be bigger than 100, right? Strictly bigger than 100. All right. So the dimensions are different. Therefore, they're not even isomorphic as vector spaces. So they're certainly not isomorphic as algebra. So this is so we've classified, we've shown how to classify matrix algebras, the algebras of linear operators on finite dimensional vector spaces over a fixed field. The classification is well, the vector spaces themselves are classified by the dimension, which is 0, 1, 2, 3, and so on. 0 for the zero vector space. And it's essentially the same number. It's essentially the same classification for the matrix algebras, the algebras of operators, except you say 0, 1, 4. So now my training clicks in, right? Yes, so 0, 1, 4, 9, 16. Okay, so that's fine. All right. But well, so this is the beginning of C-square algebra classification, and and there's an analogous classification which people may may have come across. Okay, for what are called groups, finite groups, finite simple groups, which means there are no. How many people know what a subgroup of a group is? Okay. How about normal subgroup? How many people know what a normal subgroup of a group is? Okay, good. Then suppose there are no normal subgroups, aside from the one element subgroup, the trivial subgroup, and the whole group. Those are subgroups after all. Okay, so they're always, those are, by the way, that might be just a single subgroup. You can't always say it's two subgroups because the whole group might be trivial. Anyway, if you only have the trivial subgroups, sometimes the whole group is called a trivial subgroup. Then it's called a simple group. And if it's a finite group, well, some finite groups are automatically simple, right? Like if you have if the number of elements is prime, then I guess it's a simple group, right? It's even automatically commutative. Everyone come across that? That's a good exercise. If you want to, you could do that. I could hand that in. Don't tell Mr. Lau I said so. Okay. Well, but as soon as you get to be not a prime, then actually that's an interesting question. If it's not a prime number, is there always more than one group? Well, probably there is. That could be a good exercise in itself to decide if it's not a prime number, is there always more than one group with that many elements, with that order, if you like. Okay, well, but certainly it's known, for instance, if it's 4 elements, then there up to isomorphism, there are 2 groups, right, with 4 elements. And they're both abelian, both commutative. You know, to me, the word abelian is real because I visited the University of Oslo, and there the math department is in Abelhuis. Abelhuis, okay? So, By the way, there's an Nobel Prize. How many people have heard of that? Good. It's awarded by. It's interesting. It's almost rhymes with Nobel, right? It's hoped that it will be a similar stature, awarded by the King of Norway. Well, one of the prizes called the Nobel Prize, Peace Prize, is also awarded by the King, the monarch of Norway. Well, so what I'm leading up to is how many people are familiar with the Little Red Book? Well, that's is this really passé, completely passé? Mao's Little Red Book. Okay. Well, you know, I'm glad to hear it. If it's gone, that's fine. Fine with me, I think. Don't tell him I said. Okay, but there's a big red book. The big red book, which is called, what do you suppose the title of this big red book is? It's called the Atlas of Finite Simple Groups. Okay, that's it. That's the classification of finite simple groups. Okay, you can look it up. Be in the library, you might not be able to take it down from the shelf. I mean, if it's not, even if you were allowed to, it might be quite heavy. Yeah, it is. Well, it's about this thick and this large by that large. It's something like that. I've seen it. Okay, I haven't tried to lift it, but so what it is a list of finite simple groups, and what we just did was make a list of finite dimensional C-star algebras, because you can take direct sums, but it's finite dimensional simple C-star algebras if you like. Okay, we made a list, and that was pretty short work. But the classification of finite simple groups, some people are still checking it. Okay, they want to be sure it's correct, because it's not that it's thousands and thousands of pages to establish it, right? And they're not all in this book. I don't think there'll be room, however large it is, I don't think there'll be room for the proof. The proof is maybe still unfolding. Obviously I'm not an expert. All right, but okay. So what's my point? Well, my point is, it's not just finite dimensional simple C-star algebras that can be classified. It's almost, now this is a vast overstatement, okay? But it's for all intents and purposes, to the man in the street, it's all simple C-star algebra over the complex numbers, okay? I won't be surprised if some experts leave the room, but that's something I hope to convey during the term, how close to being true this is. It's such a vast collection of algebras that even the mind even goes into overload just trying to fathom what it means to classify them. Okay, and so in other words, there's no such thing as a list there's a list of finite dimensional simple C-star algebras. Just numbers. There's number 0, number 1, number 2, number 3, and so on. It's just like for finite simple groups. There's finite simple group number 0. It's not the one with 0 elements necessarily. It might be the one with the finite simple group number 1, finite simple group number 2. There's a list, a discrete list. Countably many of them, and they're just listed. You have to check that every group is isomorphic to one of the groups in the list, every finite simple group, and the ones in the list are all different. Okay, otherwise it wouldn't be really a classification. But for some classes of C-star algebra, some classes of simple C-star algebra, you can do the same thing. It won't necessarily be countable, but to be a nice parameter, and you can just associate with a family, with the parameter, you can associate algebras in this class. And every algebra in the class is isomorphic to one of these and to only one. So you've classified the algebras by parameters. I mentioned Grimm's name already. Well, that's what he did in his PhD thesis. He showed, in fact, that there's a nice class of C-star algebras that can be classified by a parameter. In fact, the algebras are given as they're constructed. You can construct the family of algebras according to this parameter, which is, by the way, a point in the Cantor set. Everyone know what the Cantor set is? Okay, 0, 1, the set 0, 1, sequences of zeros and ones. In the computer age, everyone should know what the Cantor set is. They would automatically, okay. But so Grimm, for every point, for every sequence of zeros and ones, Grimm constructed a C-star algebra. And then it turns out that every C-star algebra in a certain class can be defined axiomatically. Every C-star algebra in that class is isomorphic to one and exactly one of these of the algebra so that you have a Cantor set, a nice Cantor set of isomorphism classes. Algebras. Well, that's just as good a classification as of finite simple groups or of matrix algebras. You have a nice parameter, well-behaved parameter. It doesn't have to be discrete. It's a continuous parameter. And furthermore, if you have the same thing was done by a little later by a team of people. I made a reference in my emails from January to the rotations, okay? Rotations on the circle. Every one of those you associate an algebra. And if you look at the rotation from 0 to pi, all those rotations give you, well, in the irrational case, irrational multiple of 2 pi, it's going to be a simple algebra, simple C-star algebra. And you look at this abstractly defined class of algebras, every one of them is isomorphic to one and only one number. So the one parameter set, gee, I'm glad I brought my own chalk, but don't have time to fish it out. Here's a piece which is an eighth of an inch long. That would be enough. Or an eighth of a minute, which is left. Okay. So if you look at the Cantor set, you leave out, I like this French way of writing closed intervals. The open interval is the opposite, okay? So then it's the middle third set. So you remove all the middle third sets. That's the Cantor set, okay? So that's the Grimm algebra. And then the other parameter space goes from 0 to 1/2. Both of these are labeled the set of isomorphism classes. It's a nice list, okay? But in general, you can't expect to have a nice list of the isomorphism classes. The classification is not a smooth, well-behaved classification like this. And so what it is, that's what this course is about. Okay. Well, I think I won't overstay my. I won't try to overstay my welcome. We do have an hour, right? Okay. Well, let's. And that means there'll be someone chomping at the bit outside. Yeah. But just think about that. What is the what are we actually looking for? Well, I've given you the hint that we're looking for K0. Okay.